Yeah, it is. Good morning, everyone. I hope you had a good evening last night. Today is the last day of our first week, and we have two more talks. This morning, Sara will give her second talk on monomial ideals. And just a reminder that right after this talk, we are going to go have the picture. And I think I will find out whether it's actually in this room or we'll do it outside. Okay, so take it away, Sara.
All right. Thanks for coming again. And I think I'll go longer again a little bit. I'm sorry, I'll go a little bit over probably because I missed my middle talk. Sorry? Yeah, well, that's okay. But yeah, okay, I'll try. I'll do my best to be. We'll pretend the organizers did not hear that. Okay, so right, so I was talking about, I drew a diagram for you, and basically my emphasis was about the discrete side of looking at monomial ideals and about the homological or the characteristic dependent properties that we look at. And most of the properties people in commutative algebra care about are characteristic dependent, but most of the properties we get to play with are not, because that's much easier. It's much easier not to compute homology. So what you do is you prove something has such and such homology, and then you get on with it. You always play with that same object again and again. So I'm going to put up my diagram again. So if you recall, we had a square-free monomial ideal. Everything is square-free. I started with I, and I made the non-face complex gamma. This is the Stanley-Reisner complex. And I made the facet complex delta. So the way this worked is that if I is generated by M1 to MQ, here my facets were basically M1 to MQ. Okay, so here I'm abusing notation. Over there we have products of variables. Here facets are maximal faces, and we have the set of variables is the maximal faces. I'm just using the same notation. And here I have G1 to GT, where basically all the faces, actually, I'll write the definition as a reminder. All the sigma subset of the variables set such that sigma is not in I. These are all the faces. So I'm putting a set notation. Okay. And we have the cover complex here. So here the facets are minimal vertex covers of delta. Those are the facets, and it's delta M. This is called the cover duality. These are really the minimal primes of I. And here I have the Alexander dual. And this Alexander duality is from topology, so this is a triangulated version of it. It turns homology into complementary cohomology. But for all practical purposes in this area, we care about the dimension of these homology modules. So, and the dimensions are going to be the same. So this becomes extremely handy when you're dealing with numerical invariance of square-free monomial ideals, because they just depend on the dimensions of those homology modules. So I'm hoping to get into that a little bit today. And basically, you repeat the same thing. So in Stanley-Reisner, ideal of this complex is equal to the facet ideal of this complex, and it's called the Alexander dual ideal. And these two are complements. I'm going to just write complements here. Meaning that take a complement of a facet here, you get a facet there, and vice versa, and same here. Okay? So I'm going to start from up here, and I talked about the Cohen-Macaulay condition. So today I thought I'd do a little bit of review of things that we know are Cohen-Macaulay, and a lot of things I'll leave for exercise sets. Some of them are open questions. And then I'm going to move down here and look at the dual notion to Cohen-Macaulayness, which is linear resolution. And I'll show you what's known over here. And I thought that's a good way, basically, to go around this world of duals and diagrams and complements. And as we go around it, you'll see there are lots of open questions because people usually live here or there or live in this kind of disjointed territory. But a lot of people have asked me, like, you don't know what to work on, you don't know if what you're working on is good. Pick any problem here. Most people don't know the answers. Just try to work on it and see what you get. And you might not think it's interesting, but it is interesting to someone, and it might be the next big thing. So, and some of these problems are not, some of them are really, really hard, but some of them are not very hard. It's just that no one has ever looked at them. And some people really love combinatorics. So if you're one of them, this is your chance. All right, so the Cohen-Macaulay property, remember, I'm not going to define it again. So maybe I should say here that my square-free monomial ideal is in a polynomial ring over the field x1 to xn, and K is a field. And Cohen-Macaulay next, I will write this in orange. I was going to copy an example, and I forgot, so I will do that during the break after the picture. This very much depends on base field, which means really it depends on the characteristic on the base field. Okay, and this will play a big, big role, especially when I start telling you about what's going on around here. A lot more has been done here than for linear resolutions than for Cohen-Macaulayness. So Cohen-Macaulay, right, so we say that gamma is Cohen-Macaulay if and only if the homology of the link in gamma of every face is 0 for every I less than the dimension of that link, and sigma in gamma. And I think some of you, it was on the problem set, some of you probably did try Reisner's criterion on a few examples. You always have to compute homology for it. So then the question is, what things are Cohen-Macaulay without having to compute homology? When are we guaranteed Cohen-Macaulayness? So what is the first thing you can think of that has no homology except for at the very top? And when you take a link, it still has no homology. So no homology at the top, you think of like an empty ball, a sphere. Okay, and then also when you take links, still the same thing happens. So this is called a homology sphere. This is the definition of a homology sphere. So maybe I'll do a facet side and a Stanley Reisner side here. An N side and an F side. So homology spheres are Cohen-Macaulay. Gamma homology sphere. The definition is that HI gamma actually, I can make the definition to be the definition of the link, because the link of an empty face is the whole complex. So it's 1 if I is equal to the dimension of the link sigma of gamma, and it's 0 otherwise. And this is always Cohen-Macaulay, just by Reisner's criterion. Okay. Then there are other things on the Stanley-Reisner side that are known to be Cohen-Macaulay. So one of them that I promised I would do is vertex decomposable ones. Maybe I'll first do shellable complexes. Shellable complexes, these are the most famous example of Cohen-Macaulay ones. What does it mean to be shellable? So suppose gamma has facets F1. Actually, no. I want to order the facets. It's shellable if I can order the facets as F1 to Ft so that each one of them is meeting the complex of the previous ones in codimension 1. So I will show how that happens, but I forgot to tell you one important thing is that Cohen-Macaulay implies pure. So a lot of things I say here work for the non-pure case, but I'm really interested in the pure case. I'm going to put this up here. So if I Cohen-Macaulay, then gamma is pure. That means all facets have the same dimension. Okay, so have the same size. And it also means that delta is unmixed. So you can actually now prove this because of this complement. If all of these have the same size, then all of the minimal vertex covers have the same size. That means that means that delta or I is unmixed. That means all minimal vertex covers okay, so let me add pure everything. Okay. In particular, I'm embarrassed to say, I think part of the, I don't remember if Reisner's criterion, I think you need to assume purity, but I could be wrong. You don't need to assume it? So it follows from it? Perfect. Oh, actually, it should follow from it, right? Yes, so yeah, here's a problem then. I'm glad I asked. So problem. Show by Reisner's little y criterion gamma Cohen-Macaulay implies gamma pure. Okay. Okay, so what does it mean to be shellable? So I'm talking about pure shellable. So again, pure. That means all facets can be ordered so that facets can be ordered as F1 to FQ so that if you take the first I of them and you intersect with Fi plus 1, you're going to get something of dimension d minus 1. So this is dimension of this is d minus 1. and of course, pure of dimension D. So for example, something, trying to use the good chalk, something like this is shellable, famously, and something like this, these are the very simple examples, is not shellable. So here are two problems for you. Show the first one is Cohen-Macaulay using Reisner's criterion, or find a regular, show depth is equal to dimension. This is a small enough example. Meaning when I say show is, if you're using depth equal to dimension, you have to take the Stanley-Reisner ideal of it. If you're using Reisner's criterion, you can take you can just take the complex. And here I'm going to ask, is it Cohen-Macaulay? What do you think? It's actually the distance between Cohen-Macaulay and shellable is not very big. It's a little bit, it becomes topologically weird. Most people, when they think of Cohen-Macaulay, they come up with shellable things. So it's you know, we all know examples, but it's not like there is an abundance of examples that naturally come to mind. So this is a nice example to do, nice question to do. Is that Cohen-Macaulay? Then there is vertex decomposable ones. Oh yes, that's over all I. Thank you. For which it makes sense, yeah. Gamma vertex decomposable. So this is a stranger definition. Also ends up being Cohen-Macaulay. It just means that, so it's a two-step definition if, one, again, we assume pure, right? We're always assuming pure. So either gamma is a simplex or the empty set, empty complex. Two, there exists a vertex such that link of that vertex or del of that vertex is vertex decomposable. Which basically means you either start from a simplex, this is your last or empty set, or you can link and delete so many times that you get to a simplex or you get to the empty complex. So link, I already told you what it means. Deletion means just drop a vertex. So deletion gamma V is all the faces of gamma who do not contain V. Okay. So I'm going to pause here again and actually ask, because there are experts on this in the room, and there is another definition I've seen of vertex decomposable that assumes that if you delete a vertex, you're going to, no, wait, a shedding vertex is going to always leave you with facets or something like that. Do you need that, or is it only for the case where you have non-pure? Okay, so it's just to make life easier? Or, yeah. But just like this, you could also define it for non-pure. I mean, you don't need anything extra for the non-pure case.
For the non-pure case, we want to know that the link and the delete and don't care anything.
Okay. So the reason I'm asking this is because everything I'm saying is actually really interesting also in the non-pure case, and also interesting in the mixed ideal. So I'm only sticking to the simplest case, but usually by just adding a small extra conditions, you can do everything in the more general setting. All right, here's your problem in this situation. And this one, please everyone do, because apparently it will be handy for next week. Show that this picture is vertex decomposable. You showed that this picture is Cohen-Macaulay using Reisner's criterion as a Stanley-Reisner complex. You showed that it is Cohen-Macaulay also as an edge ideal, as a facet complex. And now you're showing it's even stronger than Cohen-Macaulay. It's a vertex decomposable. Okay? Yeah. Yes. Yeah, otherwise it's not very interesting. Yeah. V. Oh, yeah. V. Oh, V not in the. Oh, it's even worse. Yeah, thank you. This is V not in sigma. Yes, that's a very good catch. Thank you. Yes. Yeah, that was also an important thing that was part of this narrative here. Again, thank you. Now, do I do a different color here? It's so, yeah, so. Gamma VD, then gamma Cohen-Macaulay. I'm doing Cohen-Macaulay things on this side. Okay, so I filled up one board. There's lots more. There is constructible things. There are pseudomanifolds to look at, simplicial spheres. Then there are these conjectures. There was like Stanley's partitionability conjecture about if you can partition a simplicial complex in a certain way, it's going to always be Cohen-Macaulay. And that was really cool because, you know, it's a very discrete kind of condition. And the counterexample that was given was very big and very strange. People were working on it for so many years. So there's lots and lots of stuff going on and on. This is just a sample. Let me talk a little bit on this side. On this side, we have the very first thing I can think about is whiskering. Take any simplicial complex. So whiskering was done for graphs. I'm going to just do the simplicial, the general case. Take any simplicial complex. And I'm picking this on purpose because it's dimension more than one. Also, it's very not unmixed. It's very mixed. It has minimal vertex covers of size 1 and 2. It's not Cohen-Macaulay. Then what you do is you whisker it. That means to each vertex, you add a new edge. And you don't even need to whisker it like this. You can even do this. You can add that. Or instead of this here, you could have added this. So it's whiskering or grafting. So no matter how bad this is, by adding those facets or adding those leaves or adding those generators to your ideal, the result is always Cohen-Macaulay. And actually, recently we showed with a bunch of people, including Adam, that in fact, when you do this, and I think we rediscovered that in another paper, when you do this, you're going to actually get a sphere, homology sphere. Yes.
So we said that the green guy was not Cohen-Macaulay, right?
Yeah.
But isn't that a whiskering of just
No. What is the whiskering of a
The
line?
green guy should be if I understand what you are drawing.
So the green guy was this.
Yeah. And so if you just take.
So it's the ideal A, B, C, D,
Yeah.
A, B, C, comma, C, D. So this is C intersect, for example, A, D intersect A, B, D. This is the primary decomposition. It's mixed. Sorry, who was asking me? Yeah, there you are.
Right, but so if we just take the complex BC, then
Yeah.
that guy that we've in green that we have, if I understand what you've been drawing in red, should be a whiskering of
oh.
BC, sorry, not BD, sorry, BC. It's just it's graph.
Which is the one?
BC, sorry, just the line segment. Yeah. And
Yeah.
we can graph the triangle above that, and then we can graph, or we can whisker the line CD to that as well. And then that's a whiskering of the line segment, so it should be called McCall.
Who should be called McCall?
The guy that we started with originally.
No, because for whiskering or grafting, the first condition is that you have to cover all of your vertices. If I'm starting with, let's start with BC. Maybe this is for the problem session.
Okay.
Yeah, actually, this is a great problem for the problem session. All right, so you get to tell me the statement of the problem. Yeah, go on. So Y is this picture itself, am I correct? Not whiskered or grafted. Is this what you're asking?
I guess so, yeah.
Yeah.
Yeah, because you're saying that give me any simple complex, if you whisker a graph, that you'll get something called Macaulay.
Yes.
And I'm yeah. Okay.
So the answer is that, yes. So is this the whiskering or grafting of anything?
Yes.
Okay. So partial answer to that, or maybe I should give it later, but partial answer to that is that whatever you whisker or you graft, there are two things you have to follow. One is that you do not, once you use up a bunch of vertices, you never touch them again. Secondly, it has to localize. It has to hold for all subcomplexes. So it's a localized property. This is a depolarization. Okay. Okay. So like I said, it ends up that is there another question? Yeah.
Going back to good on top, is there a line like pointing upwards?
No, I didn't. I erased it. There used to be two lines because I had to use up every vertex. Then I replaced it with, yeah. So it could have been also these two. Yeah, once you want to whisker or graft, once you want to do it, you really have to do it to each vertex. You can't leave any vertex alone. Okay, so maybe I'm going to stop on this area, but I do want to actually put some questions out there now that we have these. These are mostly open questions. That doesn't mean no one knows the answer. I don't know the answer. So for one thing, one thing is kind of reality that a lot of people either live on this side of this sphere or on that side of the sphere. They don't really necessarily, people don't work on both sides. So it's quite nice when you get to learn the techniques on this side and apply it here and so on, because this side is more about how are the generators of an ideal behaving. And like we discovered that, and this was actually known, we didn't really do anything big. We just educated ourselves that when you whisker, actually you're just getting a homology sphere. This is about the best thing you can do for making Cohen-Macaulay things on this side, okay? And ends up all you're doing is that. So I have no idea, or maybe someone does have an idea. Maybe I have an idea and I just forgot about it, but I was thinking about it today. I don't think I know what shellability means here. Adam, do you know what shalability means on this side? Okay. I don't know what vertex decomposable means on this side. Okay. So here are very nice. I'm going to put them in red. Problem. What are the facet complex counterparts of shellable or vertex decomposable? Oh, here's another question. Actually, I'm going to put another question here. Sorry, I'm messy. We're going to again write these tidily afterwards, but I like putting them near the topic. Here's another problem. Is every graph shellable? Like if you think of a graph as a one-dimensional simplicial complex. What graphs are shellable? I don't mean independence complex of a graph or anything fancy. I just mean take the graph. Because I mean, they all meet in vertices always, so. All right, so this is on, this is one board on the combinatorial Cohen-Macaulayness. Okay, are there any questions here? Okay, so the next thing I want to talk about is travel all the way down here. So it turns out that being Cohen-Macaulay is equivalent to being, I-dual having linear resolution. So this is known as the Egan and Reiner criterion, John Egan and Vic Reiner. And I didn't know if I would be able to do this, but Claudia talked about Betty tables and regularity and everything, so I can. So Egan and Reiner. Again, in the realm of square-free monomial ideals, I is Cohen-Macaulay if and only if I-dual has linear resolution. So what does that mean? So yeah. Yes, that's a very good question. Yes. How far are you? Basically, that is really the question, right? How far are you from anything? Like one question I usually deal with is either that or how far are you from linear resolution? How far are you basically from anything nice? If you can measure that, that's a great contribution. For anything nice means the things that I have up here are nice. You can do them, you can program them. Okay, so what does it mean to have linear resolution? It means you can write, so suppose your I-dual is generated by, say, U1 to UT, okay? So it means you can write a resolution. So let's discuss this a little bit before I write my resolution. So my I is Cohen-Macaulay, that means it's unmixed. That means all of the generators have the same degree. So all these facets have the same degree, which means all the facets, which means, sorry, I said this all wrong, back up. That was the other side. It's Cohen-Macaulay means all the minimal primes have the same height, means all the minimal vertex covers have the same size, unmixed. That means this is pure. Delta M is pure, right? So when I is Cohen-Macaulay, I Cohen-Macaulay, this becomes unmixed. This becomes pure. This becomes, which means this becomes pure. And my ideal is then the facet ideal of something that is pure, which means it's equigenerated. Everything has the same degree. So these all have the same degree. So that means when I write the resolution, so I have T things, and I want to resolve that. So the first thing I do is I need T copies of S, my polynomial ring, and I need to twist it by the degree of my syzygy. In this case, it's just D, so it's S minus D. And I need T copies of, oh, I put it here. Okay. So this much is just guaranteed. You always need to be in the same degree to have linear resolution. You need to be equigenerated. But then after that, you're also guaranteed that you're going to be then next S minus D minus 1 to whatever degree it is going to be. And then S minus D minus 2 to whatever the number of minimal generators are. So it means your growth is always linear. And the Betty table looks like this. So I don't know what it's D minus whatever it is. Imagine this is the correct twist of D. And the Betty table is like this. And everything else is 0. Okay? That's a linear resolution. Okay, so there are a couple of things I want to do. First of all, I want to tell you about the adventures of finding combinatorial criteria for ideals having linear resolution, but I also do want to mention Hochster's formula. And I do hope to touch a little bit upon topology and homotopy theory and the kind of things you do to find Betty numbers, which are these guys. That all goes in this area. So the dual side of that, I mean, this side already has a lot of topology in it because of Reisner's criterion, and this side is even more because there are just so many different ways to calculate Betty numbers using topology. So how about I first tell you about, I toss a coin and I'm going to tell you about Hochster's formula. So how about I do Hochster's formula here? So how to find Betty numbers using simplicial complexes. So actually, I'm going to do a board here just on this, and I will stop at the end of the board. This is a long, long, long story, but I kind of made, like the title I made up right now on the spot, because this is more than Hochster's formula. So I'll stop at the end of the board, but I'll start with Hochster's formula. So the first thing to know in this area is that when you work with any monomial ideals, and it is enough to work with square-free monomial ideals because of polarization, you can actually break your Betty numbers down into, from graded down into multi-graded ones, okay? So maybe I should put that on a lower board, or maybe here. So no, I'll put it there. So Betty numbers, so suppose you have your I, square free monomial ideal, beta I j of I can simply be enumerated as sum of beta I m of I, where m belongs to the LCM lattice of I. Okay, so actually you can say where m is any monomial, but it turns out if m is not in the LCM lattice, you're going to always get 0. Hochster's formula gives you that. So in the end, what this means is, oh, sorry, degree of m is j. I'll translate what is the LCM lattice. It's just a set of monomials. What it means is that when you want to calculate your Betti numbers in every degree, you just look at monomials in those degrees, and then you find Betti numbers on those monomials. So you want degree 2, you find all the degree 2 monomials in your LCM lattice, and then you calculate Betti numbers at those degree 2 monomials. So that computation is then very much dependent on what topological object you're looking at. And this changes all the time. And then you change your object all the time based on what you want to do and what you want to achieve. So first thing, what is the LCM lattice? So if LCM of I is the poset or ordered by divisibility of all LCMs of minimal generators of I. Okay, so this is a partial or ordered set. It's finite. It's a finite lattice. At the very top of it is the LCM of all the generators. And at the bottom of it, you can stick a 1. Okay. And it itself is one of the objects you can use to find multigraded Betti numbers. Okay, so the question is really how to calculate these. So people who do combinatorial resolutions are really, this is what they do. They find these. So Hochster's formula tells you that. Hochster's formula. So it says that beta IM, okay, so from now on, everything I say is probably off by 1 or -1, or maybe even 2. So first of all, I'm going to do S mod I because that's how it's done. My chances of error are less. Remember, we always live over a field, so it's the dimension of the homology module of the dual Stanley-Reisner complex, where you look at all the faces whose monomial label, sorry, I'm trying to translate from a different world, divides M. So maybe I should gamma dual M. Let me first get my I's and is it I -1? Hochster's formula. I minus. Oh, no. I should have done link. Okay, I'm very sorry. Link. This is also correct, but then I should use gamma. There are 2 versions of this. I'm going to also only use one version because the other one has a stranger index. So this becomes I -2 of link in gamma dual of M complement. Where here, when you're, okay, so here when you're looking at M complement, you mean the face of M. That means the set of variables that appear in M complement, okay, over K. I hope from this you get that there exists a formula, okay? Okay, so this is pretty much everything you see to me is Hochster's formula. Everything else you do with combinatorial Betty numbers is some version of Hochster's formula. So as you can see, Betty numbers and resolutions, again, depend on the base field. Okay. All right, I'm gonna, because I do want to talk about, okay, first of all, how much time do I have? 5 minutes? Okay. So, okay, during the problem session, I'm gonna write a problem for you. So, let me write, sorry? Yeah, of course I'm gonna prove that. And then in the remaining time, I'll talk about linear resolutions. Now, I just wanna give you, because I did not fill a board. Okay, here's what I'm gonna do. Here's a general idea. Beta IM of I is H something tilde, sorry, dimension K of some topological object over K. Okay, this O here is some topological object. And could be the Taylor complex, Ljubeznik complex. It could be some Morse complex. What takes you between all of these objects is discrete homotopy theory. Things like collapses and so on. I mean, discrete just because we're doing combinatorics. But what it means is you change a shape, but you do not change its homology. And the homology is what gives you Betty numbers. So you're given a huge shape, and you're saying the homology of this is going to be your Betty number. Your shape has dimension 122, but you know your projective dimension is 2. So you know you don't have any bigger Betty number than 2, right? Any bigger homology than 2 or 3 maybe because of whatever that index is. So what you do is you use homotopy theory, and there are many things like collapses and so on, to just make this shape smaller and smaller because it has a lot of extra things in it that don't contribute to homology. They're just there, okay? And there's lots of things you can use for that. So just take that as your very higher level introduction to combinatorial resolutions, but generally that's the idea. And I will have a couple of examples for you to do, maybe even using the LCM lattice for the problem session. All right, so here I told you, I'm going to tell you a couple of cool things. I'll tell you 1 or 2 cool things, maybe 1 cool thing, and all the things that have been tried to generalize it. And that's Feuerberg's result. I'm going to write it in red. I told you that resolutions depend on characteristic of the field, but it turns out if delta G is a graph, so actually, okay, so facet ideal of a G, where G is a graph, has linear resolution. If and only if the graph G is co-chordal. Okay, co-chordal means if you make, I'm going to put this in quotes, so I'm not going to write down the definition. If you take all the non-edges, the edges that are not there, you make that graph, its biggest cycle is going to be a triangle, okay? So biggest induced cycle will be a triangle. This is highly characteristic free. It's only combinatorial. This has so many attempts of generalization in higher dimensions. And what it really comes down to is characterizing the vanishing of homology, but you can't do it if you don't take the characteristic of the field into account. So you keep getting closer and closer and closer to characterizing all ideals with linear resolution. So again, there's been progress, one paper, another, but you never get there because there are all these, in every characteristic, there are counterexamples of very weird topological objects like mod 3 more spaces, one of my students was doing for her thesis, where basically all the topology and all the homology you do will just fall apart because it doesn't follow any pattern. Again, it's a very good example of how things are just not, some things are not combinatorial. You really need the homology to capture them. And that's, again, a very beautiful area, just trying to capture that as much as possible. So I can't write much more here, but I can add some for the problem session. And sorry if I went over, but I tried.